Hi friends, welcome to TSAT. I'm Reshma, 2nd B.SC Computer Science from Telangana Tribal Welfare Residential Degree College from Women's Mahabub Nagar. Today I am here to discuss the concepts of electromagnetic induction from physics. Before discussing about this topic, let us recall the basic definitions. Basic definitions such as electric field and magnetic field. Electric field. What is electric field? Electric field is nothing but whenever there is a charge in the space, it has influence around it. It has influence around it, so the space around it is called as electric field. Similarly, magnetic field. What is magnetic field? Magnetic field is nothing but whenever there is a magnet in the space, it has influence around it. It has influence around it, so the space around it is called as magnetic field. It was assumed that the study of electric field and the study of magnetic field are from the different branches of physics. But later it was discovered that there is an intimate relationship between the electric field and magnetic field. Now, objective of my discussion is what is electromagnetic induction, what are the Faraday's law of electromagnetic induction, what is Lenz's law, what is self-inductance, and finally what is mutual inductance. These are the topics I am going to discuss in our class. Now let us discuss about the electromagnetic induction. Electromagnetism. Oersted, he is a physicist scientist. Oersted discovered the existence of the magnetic field due to the current flowing in a conductor. What Oersted discovered? He discovered the existence of the magnetic field due to the current flowing in a conductor. Conductor. What is conductor? Conductor is nothing but which allows the current to pass through it is known as conductor. Then Oersted observed that there is a inducement of magnetic field because of current carrying conductor. But Oersted did not tell how much magnetic field is induced because of certain current. Then Ampere, he is also a scientist. Ampere derived the expression for the intensity of magnetic field. What Ampere derived? He derived the expression for the intensity of magnetic field. Electromagnetic induction. Faraday, that it is possible to produce a converse effect. Faraday, he is the most important scientist in our class. Faraday concluded that it is possible to produce a converse effect. What is converse effect? Converse effect is nothing but reverse effect. In first line we have studied. What we have studied? Oersted concluded that the magnetic field is created due to the electric field. Then Faraday thought that why not the electric field is also created due to the magnetic field. Then finally Faraday concluded that it is possible that the electric field is also created due to the magnetic field, and this reverse effect is called as converse effect. And Faraday, he also concluded that it is possible to produce the current from the magnetic field. What he had concluded? From the magnetic field we can produce the current. Let us move to the forward definition. In the year 1831, Faraday discovered that whenever magnetic lines of force are cutting a closed circuit and induced current flows in a circuit, then Faraday discovered that when the magnetic lines of force are cutting the closed circuit, then there is a generation of induced current flows in a circuit and lasts only as long as change exists. It means the current lasts as long as only the change in magnetic lines of force cutting a circuit, and the EMF gives rise to such currents is called as induced EMF. EMF means electromotive force. If electromotive force is giving rise to such currents is called as induced EMF. Then this phenomenon is called as electromagnetic induction, which is our topic. I hope you understood about the electromagnetic induction. Let us move forward. Now let us see the Faraday's law. Let us see how he has came to such conclusion that there is a inducement of EMF. There is a inducement of EMF due to the change in magnetic lines of force cutting a circuit. Now let us discuss the two small experiments which are explained by the Faraday. Experiment number 1. Here we are seeing a diagram that let us consider a coil of wire connected in series with galvanometer. We are seeing here there is a coil and the coil is connected with the wires. How the wires are connected in the coil? The wires are connected in series connection, and the coil is also connected with the galvanometer. What does galvanometer do? It shows the deflections depends on the current. Let us consider a magnet. When magnet is moved towards the coil, the galvanometer shows deflections in one direction. It means, let us consider a magnet. If magnet is inserted in the coil, when the magnet is brought near to the coil, and when the magnet is placed in the coil, then the galvanometer starts to show the deflections first in one direction. If the magnet is inserted out, if it is drawn out from the coil, then the galvanometer starts to show the deflections in another direction. Do remember that in this experiment we are not applying any external energy sources. And if the magnet is constant, if the magnet is stationary, then the galvanometer is also constant. The galvanometer does not show any deflections. And in this experiment we are seeing a magnet here. The magnet is consist of north pole and south pole. When the magnet, by reversing the pole, now repeat the same procedure of previous by reversing the poles of the magnet. When the magnet is applied, same procedure, then the galvanometer which is connected in the coil, it shows the deflections in reverse direction from the previous. It is about the experiment number 1. What we have learned from the experiment number 1? If the magnet is stationary, the galvanometer is also constant. The galvanometer shows the deflections when during the motion of the magnet. It is about the experiment number 1, and I hope you understood. And let us move to experiment number 2, which is explained by the Faraday. And in this experiment what we are seeing, there are two coils. Let us consider a primary coil. P is connected to a battery and secondary coil is connected to a galvanometer. It means in this experiment what we are seeing, it is the primary coil, and the primary coil is connected with the battery, and the secondary coil, it is connected with the galvanometer. And when the circuit is closed by pressing the key and it broken, then the galvanometer connected in secondary coil, it shows a deflection first in one direction and then in another direction. It means, let's see the diagram. If the circuit is closed in the primary coil, if the switch is off in the primary coil, then the galvanometer which is connected in the secondary coil, it starts to show the deflections first in one direction, and if the key which is connected in the primary coil, if the switch is on, then the galvanometer which is connected in the secondary coil, it starts to show the deflections in another direction. And it is observed that no deflections is produced in galvanometer if the current in the primary coil flows continuously. It means, see, if the current is flowing continuously, in the primary coil, then the galvanometer which is connected in the secondary coil, it does not show any deflection because of there is a continuous flow of current in the primary coil. And the deflection is produced in the galvanometer only when the key is broken. It means when the primary coil apply this condition, switch off and on, then the galvanometer starts to show the deflections which is connected in the secondary coil. It is about the experiment number 2. What we have learned in experiment number 2, which is explained by the Faraday, means if there is a continuous flow of current in the primary coil, then the galvanometer does not show any deflections. It is about the experiment number 2. I hope you understand about these two experiments which is explained by the Faraday. And let us move little forward and now discuss about the explanation. Depends on the experiment number 1 and experiment number 2. In this diagram what we are seeing, there is a magnet and the magnet is having the poles, two poles, that is north pole and south pole, and there is a coil, and these lines are called as magnetic lines. See, when the magnet moves towards the coil, the flux increasing in coil. It means, let us consider a magnet, and when the magnet is brought near to the coil, then the flux is increasing the coil. What is mean by flux? Flux is nothing but number of field lines are passing through the unit surface area is known as flux. If the magnet is moving towards the coil, then the flux is increasing the coil. Why the flux is increasing in the coil when the magnet is moving towards the coil? Because at the poles the magnetic lines of forces are more. So that's why the flux is increasing in the coil. It is the reason. And when magnet moves away from the coil, the flux decreasing in the coil. It means when the magnet is moved away from the coil, then the flux is decreasing in the coil. Why the flux is decreasing? Because when the magnet is moving away, then the magnetic lines of forces are also decreasing. So the flux is decreasing in the coil. In both the cases, EMF is obtained during the motion of the magnet. In both the cases, what we are observing is there is obtained of electromotive force during the motion of the magnet, because we are moving the magnet far away and near. So there is a obtained of electromotive force in the coil. And in experiment number 2, from experiment number 2, what we have learned is when the current increasing in the first coil, there is a gradual increase in flux. It means, let us see, it is the primary coil. If the current is increasing in this coil, primary coil, then there is a gradual increase in induced flux, and there is a gradual increase in induced flux. When current decreases in the first coil, there is gradual decrease in flux. It means when the current is decreasing in the primary coil, then there is a decreasement of flux. In both the cases, there is change in flux. Means in both the cases, what we are observing that if the current is increasing, the flux is increasing. If the current is decreasing, the flux is decreasing. So the flux is changing, it is increasing and decreasing. So there is a change in flux, and this change in flux is linked to the secondary coil and produces induced current. And the flux is changing in the secondary coil, and there is a production of induced current in the secondary coil. From this explanation of experiment number 1 and experiment number 2, what we have learned means, if the current is increasing, then there is a increase in flux. If the current is decreasing, there is a decreasement of flux in the secondary coil, and which is linked with the secondary coil. And I hope you understood, and let us move. Now discuss about the Faraday's law of electromagnetic induction. Up to now, what we have seen, we have studied about the electromagnetic induction. Now we are studying about the Faraday's law of electromagnetic induction. It means which is explained by the Faraday, the electromagnetic induction we are studying now. Following are the two laws of electromagnetic induction. There are two laws of Faraday law of electromagnetic induction. First law. Whenever the magnetic flux linked with a circuit is changed, an EMF is induced in the current. It means the magnetic flux is changing in the circuit, then the EMF is induced in the circuit. Means if magnetic flux is changing, then there is a production of induced EMF in the circuit. Here Faraday himself has given the magnitude of induced EMF because of certain fluxes, and it is known as second law. Now we are studying the second law, which is given by the Faraday. The magnitude of induced EMF is directly proportional to the negative rate of variation of magnetic flux linked with the circuit. It means the magnitude of induced EMF is directly proportional to the negative rate of the magnetic flux. And these are the Faraday's law of electromagnetic induction. And now see phi. What phi represents? Phi represents the magnetic flux, and E represents the electromagnetic induction. So the formula for the electromotive force is minus d phi b by dt. Phi b represents magnetic flux, no? So there is rate of change of flux per unit time. So the formula for the electromotive force is minus d phi b by dt, and this is also known as Newman's law, and this formula is known as Newman's law. If there are n number of turns in the coil, then the formula of electromotive force is changes as minus n d phi b by dt. N means number of turns in the coil, rate of change of flux per unit time. It is the formula for the electromotive force, and in the Faraday's law of electromagnetic induction. It is about the Faraday's law of electromagnetic induction. And now discuss about the Lenz law. Lenz law is discusses in order of inducement of magnetic field, and in this Lenz law what we are observing, there is a coil and there is a magnet, and the coil is connected with the galvanometer. And the statement of Lenz law states that induced current flows in a circuit in such a way to oppose the change in the flux that produced it. It means what the Lenz law is saying? Lenz law saying that the induced current is flowing in the circuit. If the current is flowing in the circuit, it opposing the change in flux in the circuit itself is known as Lenz law. And see, let the south pole of a magnet is approach a closed coil, then magnetic lines of force increasing in the coil, then EMF is induced in the coil. Here on the face of the coil, south pole will be induced to oppose the motion of the magnet. It means, see, here there is a diagram. If the magnet from north pole and south pole, the magnet consists of two poles, north pole and south pole. Now at the south pole, the magnet is moving near to the coil, then the magnetic flux is increasing in the coil, and there is a inducement of EMF. Hence there is a inducement to the south pole because of there is a repel to south pole due to the inducement of current. And see, let the south pole of a magnet is moving away from the coil, the lines of force in the coil decreases, then induced EMF is obtained. Induced EMF means induced electromotive force is obtained. Here on the face of the coil, here north pole will be induced to oppose the motion of the magnet. It means if the, let us take the magnet, here we are seeing first there is a against repulsion, and second we are seeing here there is a movement against attraction. So when the magnet is moving away, from the coil, then the magnetic lines of force in the coil are decreasing, but there is a inducement of EMF, there is a inducement of electromotive force, and hence there is a inducement to south pole, and there is a attraction to south pole because there is a decreasing and inducement of current. And it is about the Lenz law. Lenz law is what is showing? The Lenz law showing the direction of the induced current. It is about the Lenz law. And now let us see self-inductance. The phenomenon of self-inductance was discovered by J. Henry of America in 1832. In the year 1832, J. Henry of America discovered the self-inductance. J. Henry discovered the self-inductance, the phenomenon of self-inductance. The magnetic field is established by a coil when current flows through it. The magnetic flux lines are also linked with the coil itself. It means, let us consider a coil. If in the coil, if the current is flowing, then there is a production of magnetic field and the flux lines are linked with the coil in itself. And it means if the coil is changing if the current is changing in the coil, then the production of magnetic field in the coil itself and the magnetic lines of force are linking with the coil in itself. When the current in the coil changes, the magnetic flux linked within the coil also changes. It means when the current, it is also gives the same. It means in the coil, if the current is changing, then the flux is also changes within the coil, coil, and the change in magnetic flux results in accordance with the production of an induced EMF in the circuit as per the Faraday's law. According to Faraday's law, it gives that there is a change in magnetic flux. There is change in magnetic flux and there is a production of induced EMF. If the current is changing, the magnetic flux is changing in the coil, and there is a production of induced EMF, and there is a production of induced EMF in the circuit. If the current is changing, the magnetic flux is also changing. Then if the flux is changing, then EMF is inducing or EMF is producing in the coil according to the Faraday's law. The phenomenon of producing an induced EMF in a coil due to change of current in the coil itself is known as self-induction. It means if the current is changing in the coil, then there is a inducement, then the magnetic flux is changing in the coil. If magnetic flux is changing in the coil, then there is a production of induced EMF. Then there is a generation of EMF in the coil itself is known as self-induction, and the induced EMF is known as self-induced EMF. If EMF is inducing in the coil, then it is known as self-induced EMF, and it is about the self-inductance. What is meant by self-inductance? If the current is changing in the coil, then the magnetic flux is also changing in the coil. If the flux is changing in the coil, then there is a generation or production of the induced EMF is known as self-induction. And now see coefficient of self-induction. Coefficient of self-induction, the magnetic flux phi B linked with a circuit is directly proportional to the current I flowing in a coil. It means the magnetic flux, it means phi B. In previous we have seen, what we have seen, phi represents the magnetic flux, and now the magnetic flux is linking with the coil and is directly proportional to the current. Why the flux is directly proportional to current? Because we have seen in the previous what we have seen means, if current is changing in the coil, then the flux is changing in the coil. If the current is constant in the coil, then the flux is also constant in the coil. So that's why it is the reason for phi B, the magnetic flux is proportional to the current I, and phi B is proportional to I. And what phi B magnetic flux is equals to, why we are taking equal to means, by removing proportionality we get the proportionality constant. We get the proportionality constant, that is L. Phi B is equals to Li, and L is a proportionality constant, and it is called as coefficient of self-induction, and it is about the self-induction. And now let us discuss about the mutual inductance. Consider two coils, primary coil and secondary coil. They placed near to each other. Whenever the current I1 in the primary coil is changed, the magnetic flux linking the coil changes. These changes in the magnetic flux in the secondary coil also undergoes a change. In the mutual inductance we are also seeing same. Means in this mutual inductance, let us consider two coils, primary coil and secondary coil. If the current is changing in the primary coil, if the current is changing in this primary coil, then the magnetic flux is changing in the secondary coil. If magnetic flux is changing in the secondary coil, then it undergo a change, that is there is a inducement of electromotive force, and the phenomenon of producing an EMF in a coil due to the magnetic flux it nearby coil is called as mutual inductance. It means if the current is changing in the primary coil, then the flux is changing in the secondary coil. If flux is changing in the secondary coil, then there is a production of induced electromotive force, and it is nearby coil, and it is nearby coil because we are placing the two coils near. So it is called as mutual inductance. Can you see the difference between the self inductance and mutual inductance? Means in the self inductance also, if the current is increasing, if the current is changing, the flux is changing. If the flux is changing, there is a production of induced EMF. If there is a production of induced electromotive force in the coil itself. But in mutual inductance is the change in current. If the current is changing, then the magnetic flux is changing. If magnetic flux is changing, then there is a production of induced EMF in the coil, and it is nearby coil, and it is nearby coil itself. It is nearby coil itself is known as mutual inductance. In self inductance, in the coil itself is known as self inductance. It is the difference between the self inductance and mutual inductance. And see the explanation for the self inductance. When current I1 is set up in the primary coil, the magnetic field will be produced by it. It means we have seen previous, if the current is changing in the primary coil, at that time only we are seeing that there is a change of magnetic flux in the secondary coil. So the current I1 is set up in the primary coil. Then magnetic field will be produced by it. Means if the current is changing in the primary coil, then the magnetic field is producing in the coil. The magnetic lines of force pass through the secondary coil. Means if the current is changing in the primary coil, then the magnetic field is producing in the primary coil. If magnetic field is producing in the primary coil, then from the magnetic field we are getting the magnetic lines of force. Then the magnetic lines of force are passing through the secondary coil because the primary coil and secondary coil placed near to each other. So when the magnetic field is producing in the primary coil, it releases the magnetic lines of force. So the secondary coil is near to the primary coil, so the magnetic lines of force are passing through the secondary coil. In the previous we have seen, what we have seen, phi. What is phi represents? Phi represents the magnetic flux, and here phi 21 represents the magnetic flux which is linked with the secondary coil. Why we are saying the magnetic flux is linked with the secondary coil? Because if the change of magnetic flux we are observing in the secondary coil, so we are saying that the magnetic flux is linked with the secondary coil due to the current I1 in the primary coil. If the current is changing in the primary coil, then the flux is changing in the secondary coil. So we are seeing the magnetic flux phi 21 must be proportional to I1 in the primary coil. If it means if the current is changing, the flux is also changing. So it is increasing, the flux is also increasing. If the current is decreasing, then the flux is decreasing. So they both are proportional. So phi 21 must be proportional to I1, and phi 21 is equals to, by removing proportionality we get the constant proportionality, that is M21 into I1 is called as mutual coefficient of mutual inductance, which is linked with the secondary coil, and it is the final equation. The final equation is phi 21 is equals to M21 into I1. It is known as coefficient of mutual inductance. It is about the mutual inductance. Thank you for giving this opportunity for TSAT and for tribal officials and our mentors Swati ma'am and principal. Thank you.
ఆహారం పాడవకుండా ఉంచడం ఆహార పరీక్షణ ద్వారానే సాధ్యం. మనం ప్రతిరోజు ఎన్నో ఆహార పదార్థాలు వాడుతుంటాం. అవి కొన్ని రోజులుగా మన ఇంట్లోనే నిల్వ ఉంటున్నవి కావచ్చు. ఉదాహరణకు పప్పులు, ధాన్యాలు, చింతపండు మొదలగునవి. కొన్ని